Hello everyone, today I will do a short follow-up talk on my previous talk about orbital mechanics in more or less than 3 dimensions, and I will also make a short announcement and tech overview over the Soyuz launch in a few hours with Kanopus 3IK and Flying Laptop among many other smaller satellites. Now on the orbital mechanics, I will pretty much wrap up the higher dimension orbital mechanics for now. I will then make videos about other aspects of more or fewer than 3 dimensions, and also maybe other aspects of orbital mechanics and obviously spaceflight, since that's what I'm mainly talking about. But I'll probably rarely talk about higher dimension orbital mechanics after this, since this will pretty much wrap it up. Now, das etwas, fellow German, so you might not be able to just read the comment, but he basically asked me to talk about orbital mechanics with even higher exponents in their gravitational equation. Now, today I will be showing some simulations of these, and I will explain why these are so similar to the 2 and 4 dimensional orbital mechanics. Now, to see why exactly orbital mechanics behave this way, we can look at 3 dimensional orbital mechanics first, which actually turns out to be rather simple and a rather special number of dimensions, that is with a inverse square law for gravity, because if you want to go deeper into orbital mechanics, even just two-body problems, you will need to solve a basic differential equation, or basically it already has been solved and you can put in certain parameters. But it's known as the Weis-Weaver equation, and what you basically do is you take the conservation of rotational inertia, which is essentially Kepler's third law, and the conservation of energy, and you try to put them together in one differential equation, and the solution of that is the complete motion of an object in a two-body problem on a Kepler orbit. It does confirm that the orbit is an ellipsis with the common center of mass of the two bodies of the two-body problem in one of the focal points, which you already knew from Kepler's 3 laws. But it also tells you exactly how fast the object is moving and when it will be where, and how the orbit would change if you applied any momentum to the object. But more importantly, it gives you a mathematical reasoning behind Kepler's laws, which were based on observation alone. And while solving this differential equations, you get the formula for gravity, which follows the inverse square law, and it turns out that the formula for centripetal force or centrifugal force, depending on which kind of frame of reference you're looking from, also has a square in it. That is, the centrifugal or centripetal force is proportional to the velocity squared, or the radial part of the velocity squared, and that kind of cancels out with the gravitational part. Now, the exponent of the gravitational function actually makes the orbit basically less stable. If you think about it, if the object gets closer to the other object, the gravity gets stronger and pulls them even closer together, so the gravity gets even stronger and they get even closer together, or the other way around, if it drifts apart, the gravitational pull gets weaker. So that part actually makes the orbit less stable. The higher the exponent is, the stronger that effect is, and the less stable the orbit would become. And on the other hand, the centrifugal force makes the orbit stable in a way, since The closer the objects get, the faster they move, and thus the centrifugal force gets stronger. And the closer they are, the smaller the radius or the distance is, and that also makes the centrifugal force stronger. Or, of course, centripetal force, depending on which frame of reference you're looking from, but the centripetal force is at the same time gravity, assuming a circular orbit. So this is a slightly more complicated discussion, and it's mostly about terminology, so I'm not really that interested in it. Now, since the velocity component of the centrifugal force, for lack of a better description, basically cancels out with the square law or inverse square law of gravity, with the remaining distance component in the centrifugal force, the orbital mechanics in 3 dimensions with an inverse square law are stable, but just so stable, but also dampened and thus periodical, and the orbital path is also symmetric. Now, if you look at a lower exponent in the gravitational equation, as in, for example, a 2-dimensional orbit, then the effect of the distance component in the gravitational equation gets less extreme, and thus the orbit becomes more stable, but its argument, or the argument of perigee and the argument of apogee, also start to shift, and they start to shift more the lower the exponent for the distance component in the gravitational equation is. And if you look at a gravitational equation with a higher exponent, then the effect of the distance in the gravitational function becomes stronger, or if you're talking about one point, the gravitational gradient becomes stronger, and thus the orbit becomes less stable, which in case of 4 dimensions and an inverse cube law means it becomes a little bit less stable than the just so stable orbit of 3 dimensions, which makes the orbit overall unstable, and this trend just keeps going with higher dimensions, and it starts getting a little boring, since they start looking very similar. If you compare, for example, 10 dimensions to 11 dimensions, you pretty much get the same image. Once an object drifts a little bit away from the other object, the gravitational pull gets a little bit weaker, and the orbit is no longer stable, and the object drifts away, and relatively soon it's in a place where the gravitational pull of the other object is pretty much negligible, and thus drifts on forever. So basically the escape velocity is just about the velocity of a circular orbit, and since obviously in a circular orbit the distance is always the same, so the exponent of the gravitational function doesn't matter that much, in a close to circular orbit it behaves still rather close to a 3-dimensional orbit. So in this case it actually does a bit of a spiraling motion, since it stays relatively close to the 3-dimensional orbital path while spiraling outwards, which looks kind of weird if you're used to 3-dimensional orbital mechanics, since you know in 3-dimensional orbital mechanics the orbit is always symmetrical, and thus any escape trajectory has less than 180 degrees between its perigee and its final stretch, which it doesn't really have a final point, obviously. It goes on forever and ever, but at some point it's the direction between the two objects doesn't change much anymore. It approximates one basically final direction between the two objects, and that's usually less than 180-degree turn from the perigee. Now, I've also shown some simulations with a gravitational function where the gravity is independent of the distance between the objects, which seems very weird at first, and it's also really purely hypothetical because this would be the case in a one-dimensional universe, but in a one-dimensional universe, obviously, you can't have a two-dimensional orbit, but it's still rather nice to look at and kind of interesting, but it's actually quite similar still to the two-dimensional orbit. Now this wraps up my talk about orbital mechanics in more or less than 3 dimensions. Now to the announcement of today's Soyuz launch. I will be covering this launch live, and it's kind of interesting for me. The Soyuz launches a lot of smaller satellites into a sun-synchronous orbit, that is a close to polar orbit, that is designed so that the tidal forces pull the orbital plane such that it stays in sync with the yearly orbit of the Earth around the Sun, meaning that the orbital plane in relation to the Earth to Sun direction is always the same. So, for example, you can have an orbital plane that is always perpendicular to the direction towards the Sun, and thus you can have a satellite that is always in sunlight and always observing the day-night line, the morning and evening line of the Earth's surface if you have an Earth-observing satellite. Now, many of these satellites actually are Earth-observing satellites, such as Kanopus 5IK, for example, which is the main satellite, if you will, the biggest one and the one that the launch contract was initially formed around. It weighs about half a ton as part of the Canopus Earth observing fleet, and it is mostly meant to detect small fires. And the other really interesting satellite for me is Flying Laptop, because Flying Laptop, while I wasn't directly involved in it, it's a rather long-running project, of course. Building a satellite starts a long time before it is actually launched. But it is built at University Stuttgart, where I study at the Institute of Spaceflight Systems. And it's a slightly above 100 kilogram satellite that mostly has two purposes, or actually mostly one purpose. It's mostly a technology demonstrator and technology research satellite. Its main other purpose is Earth observation, for example, for vegetation growth measurement and monitoring sea vessels, which it also has basically a naval transponder system antenna on board. But it's mostly demonstrating new technologies like the new compact high-speed board computer, which is kind of the center part of the whole project, as well as small technology experiments put on board, like a laser downlink system that will be tested for a short while. So with that, I am of course especially excited for today's rocket launch. Now, as this video uploads, the live stream should already be running, though it'll mostly be showing, well, images of the rocket standing on the pad. At this point, the launch is still a while up. Now, I hope this two-topic video was kind of interesting, and as always, thanks for watching.